So in the first part of this question, we've got some relatively straightforward redox challenges. We need to know the rules of redox. In particular on here, we need to know that the oxidation state of oxygen in a compound is -2. That's with the exception of peroxides, such as hydrogen peroxide, where it's -1. But if we remember that, we can then work out that in NO3 minus, the 3 oxygens take me to a total of -6. The overall charge on the complex ion is -1, so the nitrogen is +5 to offset that. And the nitrogen in NO is actually much more straightforward. If the O is -2, the N must be +2 to counteract it. So then we move on to some slightly more complicated questions, and this takes us into the realm of electrode potentials. Now, there are quick ways of learning where the strongest and weakest oxidizing and reducing agents are, and you can relate it to positions within the table. But to do that, you are having to remember to also check which direction the half equations have been placed in terms of their electrode potentials or their E cell values. Because sometimes they could have given this in reverse, going from -0.44 to +1.36. So I'm far happier working out what the strongest, or in this case, weakest reducing agents are each time that we do it. Now to do that, I'm going to start by using the number line. And in this sort of question, which is very, very common, where you're asked for strongest or weakest oxidizing or reducing agent, you go for the two extremes. I know that my answer is going to come from either the top equation or the bottom equation. That gives me a 1 in 4 chance, actually, even there. So I've increased my odds massively, if I remember that simple fact. But I'm going to draw the number line so we can see it more clearly. And the number line you can see on the right hand side here is always in increasing size of number from left to right. It follows in that logical sequence. So I've put my -0.44 on the left and my +1.36 on the right. Now there's a huge amount we can do with this number line, because I know that electrons are going to flow towards the more positive or the less negative. Now, because of the way we've drawn this number line, that means they will always flow from the left-hand side to the right-hand side. And we can take that a step further forward again, because that means that whatever is on the left-hand side, the species is being oxidized. Now we've got the Fe plus 2 going to Fe half equation. And we can see that that's reduction. And the table will always give you the reduction values. So if it's oxidation, I know I'm going to reverse it. So again, we can simplify this. You will always reverse the half equation on the left-hand side of the number line. When you do that and you put them together, we see that this is the equation when we put these two half equations together, when we combine iron with chlorine. Now, what this shows us is that iron is able to reduce chlorine all the way up at the top of the table. And actually, that tells us that it can reduce everything up to there. So because the iron can reduce every species on the left-hand side of the equation, H+, SO42-, Cu2+, Fe3+, NO3-, and Cl2, it tells us that iron is the best reducing agent. So I'm going to take that a step further forward. And I'm going to say that if iron is the best reducing agent, then I follow the table up on the right-hand side of the equation, and that tells me that chloride ions are the weakest reducing agent. The chloride ions will not be oxidized by any species in this table. So as a shortcut, we know that a reducing agent will always be on the right-hand side of the equation, because the equations are always provided for the reduction process, and oxidizing agents will always be on the left-hand side. For the next question, again, quite a lot to do for 2 marks. You'll notice, by the way, there is a typo on this question, so I have amended it. Hopefully you spotted that before you began. But the Fe3 plus is gaining electrons and being reduced to Fe2 plus, and the copper 2 plus is being reduced to copper. Now, the reason I've chosen those two is that the question tells us that the cell has an EMF of 0.43. That means I had to find 2 half equations where there was a difference of 0.43 between them, and that's the only situation where it happens. So once I've got that, I'm well on the way, and once again I can draw out my number line. So I put my number line in place, and I can see here that I've got my copper half equation and my iron half equation. The copper is on the left because it's a lower number. And from there, I can also add on that because I know electrons are going to flow from, in this case, the less positive to the more positive, and as always, the electrons are flowing from the left half cell to the right half cell, that it's going to be the copper that I'm going to reverse. Now that's useful if you are trying to build an equation. But actually this is about the conventional representation of the cell. So we're going to move on now, or we're going to take a sideways step, and we're going to look at that. And I've started us off here. You can see the double vertical line, which is going to be the centerpiece of our conventional cell representation. That represents the salt bridge. And then on the left hand side, I've got my left hand half cell. I've got my copper 2 half cell. There's a couple of ways you can remember this. First of all, you're always going to have the higher oxidation state closest to the salt bridge. But there's also a really logical way to think about this. If you consider a half cell and you think about practicals that you've done, you have your copper sulfate solution, for example, you have your salt bridge dipping into it, connecting you to the other half cell, and you have your copper electrode dipped into the copper sulfate. So it makes sense that the copper 2 ions are closest to the salt bridge, because that's how they are in the half cell that we have. Same principle. On the other side, we have the highest oxidation state closest to the salt bridge. So we have the Fe3 plus there this time, and the Fe2 plus further away. But you'll notice we don't have a solid vertical line here. The solid vertical line in the copper 2 represents a phase boundary. So we've got there, for example, aqueous and solid. But here we've got 2 aqueous ions. So we separate those just with a with a comma. Now that doesn't complete the picture, because what we don't have on the right hand side on that half cell, on that electrode, is an actual solid electrode going into it. And in those situations, we will always add a platinum. And what we have here is another very good example of how you can be challenged on an electropotential question. It's lovely when you get one that simply says, what is the EMF when you put these 2 half cells together? But this is making you think about so much more. We want to identify an acid that will oxidize copper. We need to explain why. Now we can explain why using data. We're then going to suggest a possible equation, and we're going to calculate the EMF of the cell that has the same overall reaction. So my start point is to identify the half cell with the copper. And we're saying that it's copper being oxidized to copper 2. So that's having to reverse that equation. So I've started by building my number line up. I've put my copper and copper 2 half cell in at plus 0.34. But I need to find an acid which is going to go to the right of the copper 2 and copper to allow the copper to be oxidized, to allow the equation provided to be reversed. So what I can then do is take a look through, and I can see that I had a choice of Cl2, I had a choice of NO3-, and I had a choice of Fe+3. Well, NO3- is a key component of nitric acid. We can see the H+ there as well. So the H+, the NO3-, that has to be the other half cell. So from there, you can see we're identifying the acid. We've got HNO3. We're explaining why, and it's because the E cell value for the NO3- NO couple has a greater value than the E cell value of copper-2 and copper. And then we're asked to write the equation. And the equation, we take the two half cells, we identify which one needs to be reversed. Well, we've already made clear that has got to be the copper half equation. Once we've done that, we're then going to balance out the number of equations. So we multiply the NO3-1 by 2 and the copper by 3, and that will give us 6 electrons on both sides. It means I can get rid of them. And that then allows me to combine the two half equations to make the full equation that we can see here. And finally, we need to work out the EMF of the cell with this overall reaction. Well, we know what the E cell values are for each of the two half cells. So we take the 0.96 and we subtract 0.34, giving us an EMF of 0.62.